All right, hydrohalogenation reactions. Let's say we have this alkene, and we're going to treat this with, let's say, hydrogen bromide. And again, we do this at low temperatures. Let's say we do it at minus 30 degrees Celsius. And what we're going to get is one of two possible reactions. We could have H coming onto the left carbon, bromine coming onto the right carbon, or we could have hydrogen going on the right carbon and bromine going on the left carbon. These are called constitutional isomers. And if one of these products is major and one product is minor, we say that the reaction is regioselective. In other words, in which region does the bromine snap on, okay? The regioselectivity for this reaction is governed by something called Markovnikov's rule, okay? As the name there kind of suggests, he was Russian, and I just kind of abbreviate this Mark's rule, okay? Now, different textbooks have different ways of stating it, but I enjoy stating it kind of like how a Russian would say things, and that is to kind of politicize the nature of wealth and capitalism. And the idea here is that the rich get richer, okay? What does that mean? It means that the carbon with more hydrogens gets the hydrogen. Okay? So you want to think in terms of the hydrogen. So if we take a look at this molecule here, okay, this carbon here has more hydrogens. And so when this reacts with HBr, here's the hydrogen. The hydrogen is going to go onto the right carbon, and the bromine is going to go onto the other carbon. And remember that we erase the double bond, or we don't show the double bond in the products. So let's draw that. Here's our carbon. Here's our carbon. Okay. And so the hydrogen is going to show up right here. Okay. And the bromine is going to show up right there. Okay. Now, so those are that's the major product. It's the Markovnikov product. Okay. Now, so that's the basics of it. That's all you need to know about that. There is an all rules are meant to be broken. There's an anti-Markovnikov reaction we'll talk about right now. But for this class that I'm teaching you here at Danville Community College, I'm going to be skipping this reaction here. But for those of you who are interested, this goes through a completely different reaction mechanism, and you get the anti-Markovnikov product, okay? So actually the poor people get the money, and the rich people get nothing, all right? So you actually get the anti-Markovnikov product. Okay? And that's done with peroxides and hydrogen bromide. And it really only works for this. It doesn't work for HCl or HI. And it's very specific, okay? It's pretty much that's the only reaction. It's not really a general thing. All right? Now, let's practice Markovnikov's rule. All right. And I would like to do problem 9.1. I'm going to skip the peroxide stuff here in the book, but let's do problem 9.1. All right. So we've got this interesting alkene here, and we're going to treat that with HBr. And we're going to predict the products. So identify your carbons of your alkene, draw in any missing hydrogens, okay? And so the hydrogen is going to go here because that's the richer, right? So let's draw the product. Okay, the way to draw the product is essentially draw the whole framework without the pi bond. And then what you want to do is draw your additional groups in there. Now we don't need to draw the hydrogen, okay? So I'm not going to draw a hydrogen here. You can, it's not going to be marked wrong, but I'm not going to draw a hydrogen, okay? I'm not going to draw hydrogens everywhere in this molecule. What I am going to draw is the bromine here. Okay, so the bromine goes here. All right, so the H goes there, and the bromine goes here. Let's do part B. Okay, that's peroxides. All right. C is this molecule here, and we're treating that with HBr once again. All right, so you want to draw in your carbons. All right, you want to draw any missing hydrogens so that you could identify the richer carbon. And so remember, the richer get rich, so we're going to add an H here, and we're going to put a bromine on the other carbon. So when we draw the organic molecule, we can be a pro and not draw in the H's. It's not really necessary, but so we just need to draw the bromine here, okay? And we don't draw a pi bond because the carbon needs to have 4 bonds, okay? If we drew the pi bond in there, that carbon would have 5 bonds. Letter D is a exocyclic pi bond. It's a pi bond outside of the ring. And whoops, I'm sorry, that was the wrong molecule. Okay, so this molecule is treated with hydrochloric acid. Okay, so what do we get? Well, once again, draw in the carbons and draw in any missing hydrogens. Okay, carbon needs 4 bonds, so there's a hydrogen there. And then figure out where your groups go. So a hydrogen is going to go onto the carbon that has more hydrogens, and the chlorine is going to go up here. So let's go ahead and draw that product in. Once again, just sketch out the whole organic molecule without that pi bond. And then we don't need to add a hydrogen on the bottom carbon, but we do need to add a chlorine on the top carbon. Okay. 9.E is hydrogen iodide. All right, we've got 1 pentene, and we're treating that with HI. All right. Let's draw our 2 carbons. On the alkene, let's draw in missing hydrogens. Okay. And let's decide which one is richer. So this carbon on the right has more hydrogens. It's going to get the hydrogen. This one has less, so it's going to get the iodine. And let's go ahead and draw in the product here. Let's not worry about stereochemistry right now. And let's add the iodine right there at the carbon 2. So that's 2-iodopentane. All right. And part F is another peroxide. All right, so that's some basic stuff there. Now, why does the Markovnikov's rule predict the product? So why, Mark? Well, when you have a molecule like this, okay, and we treat that with hydrochloric acid, what's going to happen is that in the first step of the chemical reaction, we're going to form a carbocation, okay? Now, let me recopy this down here on the bottom. Okay. And let's very carefully think about where these curved arrows are going to go. Now, we could put the hydrogen here, okay, when this molecule becomes protonated, okay? If we do that, okay, so that's a protonation step, we're going to get this molecule here. So we're going to have that carbon and then the hydrogen here, okay? And we're going to have a positive charge right here, and we call this a secondary carbocation. All right? We have chloride floating around, and then again we can say, well, that chloride is going to pop on here, okay, nucleophilic attack, to give you the final product. All right, so you get the chlorine here, and you get the hydrogen here, okay? And that step is called attack, all right? And the other possibility is going to be down here, okay? We could put the proton on this carbon on the protonation step. If that were to happen, what do we get? So that's still a protonation. Let's draw very carefully what we form. So here's our H, right? There's also a hydrogen there from the beginning, but I'm just going to draw the H that we're adding. And we still have that methyl group. And up here on this carbon, we're going to have a positive charge, okay? We call this a tertiary carbocation. All right. Chloride, once again, is floating around, and that's going to engage the electrophile in a nucleophilic attack to give you the final product. And it's a different regioisomer, okay? Or constitutional isomer, if you want to call it that. All right. Now, we know that this bottom reaction happens. All right. For some reason, the reaction's happy to do that, and this does not happen. For some reason, something's unhappy about it. And it comes to the carbocation stability. Remember that tertiary carbocations are more stable than secondary carbocations, and we don't form primary carbocations in this class, okay? If we were to depict this with a reaction coordinate diagram, we would see that let's call this pathway A. That goes through the secondary, okay? That's going to be higher in energy, okay? So we have some starting materials, right? The methyl cyclohexene, 1-methyl cyclohexene here, and it's going to react to give you a secondary carbocation, and then that's going to react with the chloride to give you a downhill reaction like we talked about for the products, okay? And this is pathway A, all right? So a secondary carbocation is high energy, it's less stable, okay? So let's use a different color now for this, this other one. Maybe we'll choose white here. So here's reaction B. And we said that this happens because the tertiary carbocation is more stable. So if we look again at the reaction coordinate diagram, we're starting with the same product. So it's starting material, so it's going to be right here. And what happens is you're going to form a more stable tertiary carbocation. So I'll draw it there. Okay. And then the products are going to be, you know, down here somewhere. Maybe they'll be the same energy, maybe slightly different. Who knows? Okay. So that's more stable. And if I plot out where the activation energy is, I can see that the activation energy for this tertiary carbocation formation is lower than the this like light blue colored pathway. Okay, so the white is lower. Okay, so the rate's faster. Okay, and so you form the tertiary carbocation intermediate, which gives you the Markovnikov product. So that's like kind of reasoning behind it. Okay, so that's where I want to end this point now. Well, they do have some practice drawing mechanisms, and I just want to do those now. Now, to learn mechanisms, I suggest you take a blank sheet of paper, write one of these curved air reaction mechanisms in its entirety at the top, and then each day copy it. And then, try to cover the mechanism and do it from memory, and then keep doing that every day for a week. And then after that, do it once a week to keep fresh, okay? There's a lot of mechanisms here for this chapter, and we want to just get familiar with things, okay? So 9.3a states, draw a mechanism for each of the following transformations. We've got this one here, and we're reacting it with HBr, and we're forming this molecule here. Now, for anybody taking organic chemistry, you need to draw out the H line Br bond, okay? You absolutely need to do that. So I'm going to have to draw that out. So let me draw the line there. Now the reason why we draw that line is because that bond is being broken. So when we engage it, there's an arrow coming from that line, that bond, okay? So in step one, we have a protonation, and we form the carbocation intermediate. And remember, the richer get rich, so your H is over here, okay? Bromide here is going to be floating around, and that attacks this carbocation to give you the final product, A for attack. And we're not drawing the H here, okay? It's just a methyl group. Let's do 9.3b. Okay. The reaction looks like this. Oops, not double bond. Okay, and again, it's easy to type HCl on your typewriter, but it's more difficult to draw in the bond and everything. So, that's why these textbooks and so on leave that off. So remember again that the carbocation is going to form here because it's more stable, more substituted. So let's go ahead and protonate our molecule. We get a nice little carbocation there. You don't need to draw the H if you don't want to. I'm leaving it off here just to show you there's some variety here. And attack that carbon of the carbocation, and you get the product. Okay, let's do the last one, 9.3c. We've got this alkene here. HCl once again as the hydrogen halide. And so what do? Well, draw out the HCl with the actual bond there between it, and then go ahead and react, okay? And remember that this carbon on the left is going to be more substituted and therefore be the carbocation, okay? your hydrogen here. It can be drawn if you like, just to, keep track of things. And then here's the chloride attacking the carbocation to give you the final products. We call this step the attack step. All right. So now you know quite a bit more about hydrohalogenation reactions. And we will pause here and continue with the second half later.